Welcome all of you. Today we are going to discuss the next topic in our fifth unit, that is displacement current and displacement current density. Okay. So first we need to know what is meant by this displacement current and conduction current. Okay. For that, let us study a small example circuit. Consider a parallel RC circuit. Suppose I am taking a simple parallel RC circuit, RC, okay, and I am providing a supply voltage V. As these are parallel branches, same voltage will appear across the two branches. That means the voltage in R is also V and the voltage in C is also V only. Okay. Now for this parallel circuit, currents will be divided. Though the voltages in every branch will be same, currents will be divided. Suppose take the current in the first branch as I1 and current in second branch as I2. Okay. Now the current that is flowing in this resistor is called as conduction current. Current that is flowing in this resistor is called as conduction current, because this current is due to the actual motion of the charges, normal current. Okay, this current is due to the actual motion of the electric charges. So that's why it is simply called as conduction current. Generally, how we can express normal motion of electric charges current, that is I equal to V by R. Okay, I equal to V by R. This is the simple formula. And here your actual notation of the current is I1. I1 equal to the voltage across this R is V. So I am writing I1 equal to V by R. Now here we need to know about current density. What is meant by current density? Already we have defined in our third chapter. Current density J is defined as, current density J is given as current I divided by the surface area in which it is flowing. Okay, current density J equal to I by A. Now here your current is conduction current in this first branch. Conduction current means your current density will be also conduction current density JC. JC equal to, what is the current in this first branch? That is I1. Current in this first branch is I1 and your area of that resistor will be some A. So here JC is nothing but equal to I1 by A. That can be equated to, we know the point form of Ohm's law, J bar is equal to sigma into E bar. Already we have learned this in our third unit, that is sigma is the conductivity and E bar is the electric field intensity. Okay, so this is the conduction current density JC. Now we need to know what is meant by displacement current density. Okay, displacement current density is due to displacement current density. Displacement current density is generally due to time varying currents, because we are in which unit? Our fifth unit is time varying fields. Time varying means that particular quantity will be continuously varying with respect to time. Okay, the current density which is produced due to time varying current. The current density which is produced due to time varying current is called as displacement current density. Okay, displacement current, that means your I2, the current that is flowing in this capacitor branch is displacement current. Okay, because what is the general relation between voltage and current in a capacitor? In a capacitor we know that the current in a capacitor is given by I equal to C dV by dt. Okay, this is the time varying current. So here your I2 is called as displacement current. So I2 equal to C dV by dt. This is the actual displacement current that is flowing in this circuit. This displacement current is generally produced due to the time varying currents. That means it is a time varying current density, displacement current density. Now let us solve the expression for displacement current density, which is generally denoted as JD bar. Okay, so for deriving this, let us do a small simple derivation. So we have considered this circuit. We have given a supply voltage V We are considering a simple parallel RC circuit. Already we have derived this first branch current I1 is the normal conduction current that is given by I1 equal to V by R. This conduction current will result in a conduction current density of I1 by A, which is equal to sigma E bar. This is the point form of Ohm's law, J bar equal to sigma E bar, that is normal conduction current density. And now we need to solve the displacement current I2. Displacement current is generally produced due to the time varying currents. Here the voltage and current relation in a capacitor is given by I2 equal to C dV by dt. Okay, this is the displacement current which is produced due to the time varying field. Now what is the general formula for electric field intensity E? That is given by V by D. Now in the place of V, what I can write? E into D. And also we know that for a parallel plate capacitor, what is the capacitance formula? C equal to epsilon A by D. Okay. Now if you substitute all these expressions in this main displacement current equation, your current will be I2 equal to, in the place of C I am writing epsilon A by D, and in the place of V I am writing d by dt of ED. Okay. Now epsilon A by D, if I take this d as a constant outside, this will become dou E by dou T. Now this d will be cancelled, and if I send this epsilon inside, A into dou epsilon E bar by dou T. Okay, so your displacement current I2 is equal to A into dou epsilon E bar by dou T. But we already know that flux density D bar is equal to epsilon into E bar. We know that the relation between flux density and electric field intensity is D bar equal to epsilon E bar. So in the place of epsilon E bar, what I can write? I can write D bar, because epsilon E bar is equal to D bar. So we got the displacement current I2 that is flowing in this second branch of capacitor. Now we need to derive the expression for displacement current density. Displacement current density J D bar. Generally, what is the general definition for current density? Current divided by area. Current means here what is the displacement current, that is I2. So J D bar, displacement current density, is equal to, what is I2 expression? A into dou D bar by dou T by the area. So this A will be cancelled, and your displacement current density is J D bar equal to dou D bar by dou T. Okay. So from these derivations, what are the final conclusions? The final conclusions are conduction current density Jc is equal to sigma E bar. This is one formula. And displacement current density Jd bar is equal to, what is the formula? Jd bar is dou D bar by dou T. So conduction current density is sigma E bar, and Jd bar is equal to dou D bar by dou T. Okay, so these are the final expressions. This is the concept of conduction current density and displacement current density, where conduction current density is given by Jc is equal to sigma E bar, and displacement current density is given by Jd bar is equal to dou D bar by dou T. So these two formulas are very, very important. Even we will solve some problems based on them. So from our derivation, the formula for conduction current density Jc, conduction current density Jc is given by sigma E bar, and displacement current density Jd bar is given by dou D bar by dou T. Now to get the total current density, if I want to find the total current I, what I will do? Total current I is equal to I1 plus I2 according to KCL. Similarly, total current density J bar is equal to your first conduction current density Jc plus the second current density JD, displacement current density. So what is the formula for JC, conduction current density is sigma E bar. What is the formula for JD, displacement current density is dou D bar by dou T. Now any vector quantity, whether it may be some voltage or EMF something, that can be written as E equal to Em sin omega t. So here if I express this in complex form, in the place of this dou by dou t we can write j omega. And what is d bar formula? Epsilon E bar. We already know that d bar equal to epsilon E bar. So if I divide this JC and JD, JC by JD is equal to sigma by omega into epsilon. This formula is very important. What is the general formula for conduction current density JC? That is given by sigma E bar. What is the correct formula for displacement current density JD? That is dou D bar by dou T. On adding both of them, we can get the relation between JC and JD, which is equal to conduction current density JC divided by displacement current density JD is equal to sigma by omega into epsilon.